All right, welcome back to another exciting physics video here during our Corona break. Um, Today we're going to be talking a little bit about light, specifically electromagnetic radiation. Then we'll work our way into mirrors and do an example of a concave mirror today. All right, so first of all, let's talk a little bit about light. So, what is light? So light is nothing more than an electron that vibrates up and down. And so this vibrating electron produces a transverse wave. And that transverse wave could really vary in the way that it produces an oscillation. And some oscillations occur very rapidly, and some oscillations do not occur rapidly at all. And so they have very different frequencies. When we get way over here, you can have a frequency that's very, very close. That would have a lot of energy. That would be something like a gamma ray. And if we're over here, we have something that doesn't have as much energy, something like a radio wave. Now, our eyes can only see a very small portion of this entire large form of wiggle. And so that very small portion that we see is called the visible. And within the visible, we have the colors that you're more familiar with: red, orange, yellow, green, blue, indigo, and violet. Where violet light has more energy than red light would because it has a higher frequency. So things that fall over here on the spectrum would have a higher frequency, and things over here would have a lower frequency. And then things over here would have a lower wavelength, and things over here would have a longer wavelength. When talking about the wavelength of radio waves, they can be incredibly long, and when talking about gamma rays, they're very, very small. So that's a little background about light. We're going to be spending our time here focusing on the visible spectrum. Now, at the beginning, the first thing we're going to encounter is going to be reflection. So a reflective or mirrored surface causes light to bounce off of it. So if we have some surface that's been silvered or is reflective, one thing we know is that when light comes in, it's going to then leave. But one of the things I want to talk about right away is it never leaves with the same intensity that it comes in. It might come in at 100% and then leave at 90%. And then the angle that you approach the mirrored surface also affects this. When we talk about reflection, and we're also going to talk about what happens when light goes through something. So when light goes through something, this has a different name. When it goes through something, it has to be a transparent material like glass or something like that, and then it gets a different name. So when it bounces off, we call that reflection. And when it goes through, we call that refraction. And when we talk about reflection, we're going to study that in mirrors. And we talk about reflection, we're going to study that in lenses. So this will be the first week, and then this will be the second week. And then we'll kind of go through and we'll talk a little bit more about this term right here. So one thing we have to understand about is light is how it behaves or how it moves. Let's say we had a candle here. Light would emanate from the candle and travel in straight lines in all directions. And then what happens is one of those straight lines would then make contact with your eye. So I'll draw a freaky little eyeball here. And the result is you see that beam of light enter your eye. But realize if you have another light source like the sun or a light in your ceiling, light can also come from that particular item and then reflect off of the bottom of the candle, and you would see it like that as well. So light can either be created by something like a light bulb or a candle, or it can come from reflection like the sunlight bouncing off another part of an object that isn't emitting light. So light has to travel in straight lines. That's going to be the thing you really want to take away, is the fact that light has to travel in straight lines. Now, let's talk a little bit about mirrored surfaces. So when we talk about a mirrored surface, The surface can usually be identified as mirrored because it will have these little, looks like whiskers growing on the outside of it. And there are two ways that these mirrored surfaces will be curved. You can also have like a flat surface like this. So what we say is that these mirrored surfaces here have curvature. If we draw an x-axis bisecting the middle of the mirror, we can then say, what would happen if we were to continue out the curvature of the mirror and produce this big, huge circle here? Well, that circle would have some radius. So like this distance here would be the radius of this giant circle we created. If we go half of that distance, we would get to a point where we call the focal point or focusing point. Okay, so the focal point, this is going to be our first formula of many formulas we're going to encounter. We're going to say r, the radius of the curvature of the mirror, is equal to 2 times the focal length. Now this focal length is a very important point on the mirror or on the axes here. And what happens is, if you look in a mirror and the mirror is concave, that focal length is where you would flip upside down if you were looking in the mirror. This kind of curvature that I drew here is actually convex. So if we had an object, and the object could be like a candle or something, right, and it was in front of the mirror, the focal would be on the what we call virtual side of the mirror. Virtual meaning the rays will never actually cross into that side of the mirror. This is what we're going to study first. This is a concave mirror. So the angle of the mirror is actually facing the object, curved toward the object, and then the focal point will still be equal to half the curvature of the mirror. So if we say, like, I don't know, that's the radius, then half of that would be the focal length. So this point where light gets focused is called the focal point. It's always equal to half of the radius of the curvature. The easy way to remember that is r equals 2f. So what does this mean? Why do they call it a focal point anyway? It's because if we shoot a ray, or a ray leaves the object, it's either being reflected or it's producing light itself, like a candle or a light bulb. An arrow is what we use to represent an object or image. And we always start at the top of the object. And if the ray goes toward the mirror and hits the mirror, if it comes in straight, because of the curvature of the mirror, it's going to drive that ray down through this point. So the point where it crosses the x-axis, this is called the focal point. And this creates what we call our first ray rule. And so we're going to use these different rules that will help us understand how light travels when it hits a mirror. So the ray rules will always be the same for all different kinds of things. They just get applied differently. So our ray rules here are how we come in and then how we leave. So we come in one way and we leave another. So we might come in parallel and then we leave through the focal. And so that's our ray rule 1 for mirrors. Come in parallel, leave based on the focal. So like another ray rule would be just the opposite of the first ray rule, where we come in based on the focal and then we have to leave parallel. Something like that. So it's the exact opposite. Come in based on the focal, leave parallel. And then our third ray rule goes back to the fact that we can predict how light will interact with a flat mirror. So if we had a flat mirror like this one here, like the kind you look at in the morning, and you shine light at some angle theta, let's say, and it comes in and it hits the mirror, it will reflect off with an equal angle, also theta. And if you change your angle of approach, and maybe you come in at a different angle here, maybe a steeper angle based on the x-axis, it will then leave with a steeper angle. Or maybe we come in with a lesser angle, like maybe we come in like this, and then we would leave with a lesser angle like that, right? So just always, no matter what, it's going to leave at the same angle. Not so for a curved mirror, however. For a curved mirror, if I was to hit, let's say, up here toward the top, I wouldn't leave at an equal angle because of the curvature of the mirror. But there is one point on a flat mirror that is, or on a curved mirror that is flat. And so that would be this point right here, the origin, where the x-axis and the y-axis interact on the mirror. And if we hit this one spot, so if a ray comes in off of the object and hits this one spot, it will leave with an exact equal angle, and it will leave and it will come up over here. And now you might be noticing that these rays are intersecting over here. They're crossing paths. And what that does is it allows us to make predictions about what the object or what the image, okay, when we look into the mirror, we don't call it an object anymore, we call it an image. So what this does is it allows us to make predictions about what the object's going to look like when we look in the mirror. So when we look in the mirror here, in the example that I drew right here, an object behind the focal, we see that the image, and I'll label it I for image, the image is upside down, physics types say inverted. It's a little bit bigger than we started with, physics types say enlarged. And we could also say that it is real, because rays are actually intersecting with each other. So we would describe it in this way. And then we could also count over to get the distance of the image and the height of the image, and it would be negative and all these good things. But this is what we call ray rules. And they never change. So we always come in parallel, leave based on the focal. We come in through the focal and then leave parallel. And then last but not least, we come in based on the origin, and then we leave at an equal angle. So these are our different ray rules, and we can use these ray rules to help us figure out how light will travel when it interacts with an optical instrument such as a mirror. So I think I'll stop there since this has been kind of an overview, and then I'll do an example of a problem here and another video in just a moment.